Hi and welcome back to Bytes and Bits. I'm Bob Grant and this is the second lesson in our Learn to Program Asteroids course. In our last lesson we got as far as modelling the vector graphics in our program and then developing some software to animate and draw those vector graphics, so we can now place a vector shape anywhere on screen and rotate it to any direction. So now we need to start looking at getting these shapes moving around the screen and then adding some asteroids in so we can start developing the rest of our game. So let's get straight into that. So just to remind ourselves where we got to in the last lesson, I've loaded up the code from last lesson into TIC80, and if I run that with Control R, we can see then as we go in we've now got the ability to draw our vector shape. So we've defined our vector shape in our player ship object, and we can now pass that into our draw code, and that will draw the shape and allow us to rotate it in any direction. And again, we're going to be using the same code then to handle our asteroid objects as well. We have to have a look now at the actual finished game, or at least the BBC Micro version, which we're in effect copying. So if we come into our game, we can see then if we use our thrust key, it moves our ship in the direction that it's pointing. But we can, if I can just make sure I don't get hit by this ship here, but we can then, as we're moving, we can rotate our ship and then thrust in a separate direction. So the actual velocity our ship has got is actually separate from the thrust vector that we give it. So when we press thrust, we add velocity in the direction we're pointing, but we can then turn our ship and thrust in a different direction, and that then changes our overall velocity. So we're going to have to model this then in our code. Quite often the best way to model things in our software is to actually mimic the real life situation. So if we consider our player ship and it moving, that movement then can be modelled as a velocity. And if you think back to your physics theory, a velocity is a vector quantity. So it has both a magnitude and a direction. So in this example here, we can model our player ship's velocity as the green arrow. So the length of the arrow models the speed or the magnitude, and then the angle with the x-axis, because remember our angles are being measured from the x-axis in our software, that then gives us the direction. But we also know that once the ship is moving, we're then able to rotate the ship and apply thrust in a different direction. So we have to be able to model that in our system as well. So this acceleration is really just simply adding a new vector, so an acceleration vector, onto our velocity vector. And that will then give us a new resultant vector, which is the new overall velocity of our player ship. So within our software then, we're going to have to be able to model these vector quantities and then have some sort of way of adding them together so that we can change the velocity using this idea of accelerating in a new direction dictated by the way the ship is pointing. So if we come back into our code and then look at our player ship definition, so we've got our position, rotation and so on at the moment, but we now need to add into this a velocity, and we're going to make that equal to another Lua table. So we're going to mimic it as an object, and this is going to then have a speed, which is going to start off at 0, and a direction, which will be the angle at which our velocity is directed. So we've got that in there, and again we need the comma after that curly brace. So we now have our player ship model. It's got its position and its motion velocity. Rotation, of course, is the one which tells us which direction it's pointing in. And let's just reset that back to 0 after our testing. The rotation speed then tells us how fast it rotates when we press the left and right buttons. And of course, we've got the vector shape defined by these points. So we now need to do some functions which are going to be able to deal with velocity. And really what we want to be able to do is we want to be able to pass in one of our vector objects. So again, they're all going to follow this same format. Some of them will have more or less attributes inside them, but they will all have this position and this velocity. So if we pass one of these objects to our function, we want it to have a look at the position, use the velocity to update that position, and then send us back the new position after it's been moved. And that way we can just simply use the same function over and over again for all of our different vector shapes as they move around the screen. To calculate these position updates, we're going to have to do a bit more vector algebra. So let's have a look at a velocity. So we've seen already that our velocity can be drawn as a vector. So we have an arrow representing that, and the length of the arrow represents the speed, and the direction of the arrow then represents the direction our velocity is taken. And again, we're always measuring now from the horizontal x-axis, and with our tick 80 then, we're looking at positive angles being in a clockwise direction. So this particular angle here is probably going at about 45 degrees. Our position information, however, is stored as x and y coordinates. So we're going to need to break this velocity vector down into two component parts, one horizontal part and one vertical part. These will then give us our horizontal speed and vertical speed, and we can use these values to simply update our position information. Well, of course, we need to work out how large these two component velocities are. And to do this, we need to use our sine and cosine functions. And the equations we'll get then is that our horizontal speed is our total speed times the cosine of our direction, and our y speed is going to be our total speed times the sine of our direction. So that should give us enough information to complete the coding for our function. So have a go at that, and I'll see you in a few seconds. So here's our code then for this move function. And I've called mine, so I'm moving a point by a velocity. And it's bringing in then as one of its parameters then is the object which we need to move. And again, that's going to be one of our shape objects. So it's going to have its position and velocity components within that main object. So what we're doing here is we are working out our two horizontal and vertical component speeds. So I'm creating a local variable to hold my x speed. So it's my object's velocity speed times the cosine of this velocity direction, and then my vertical speed then is again just now the same thing, but this time taking the sine of our angle. Our new position then, we're making that as an object with its x and y attributes. And we're using the existing, so the incoming position information, and we're just simply adding on both the x speed, the horizontal speed, and the vertical speed onto those positions. And that will then update our position by this velocity vector. And then all we're doing at the end then is we are returning this new position object. So again, we've made our new position into a position object, and we're returning that back to the calling function. So to actually get our player ship to update then, if we come up to our main tick routine, okay, so this is our do play game. So this is our tick function which will run while the game's playing. And all we're doing here is we're taking the player ship position object and we're updating it with the value that gets returned by our move point by velocity function. Yep, so we do move point by velocity, we give it our player ship object, so it's going to extract the position information out of that and the velocity information, update the position using that velocity, and send that back to us as a new position, which we're then catching and putting it into our player ship position. So that will update our player ship position. So let's have a see if that works then. So if we go up to the top here, we've already created our velocity object inside our player ship. So what we can do is we can set it to be a speed and give it a direction. So our direction at the moment will be 0. So that should move with speed 1. And again, I don't know how fast that's going to be, but we'll see in a second. And that should then be going horizontally to the right. So if we run that code then, we now have our player ship moving. And we could come back in here then, and if we give it a direction, so let's give it a direction of 1.5. So that should be almost 90 degrees going down the screen. And let's run that and see what happens. And there we have our ship now going down the screen. So we've got the code we need now to be able to pass in something like our player ship. Our function uses the position and velocity information and will send us back the updated position. So we can now move objects around the screen. So the next task we need to sort out then is how to add a thrust key to our player ship so that we can actually press a button which will make the ship actually move. And that will simply then accelerate the ship in the direction the ship is pointing. Now, to be able to do this, again, we need to do a bit more of our vector mathematics, where we now need to be able to add a velocity to another velocity. So when we press the thrust button, we will have an acceleration velocity, which will be in the direction the ship is pointing, and we'll then need to add that to the ship's current velocity to give us a new overall velocity, and that involves then, as we said, adding two velocities together. So let's have a look at how we do that. We've already considered our velocity being a vector, and we can represent that by a line as shown here. And we know then that we can break that into two component velocities going along our x-axis and our y-axis. If we then decide that we want to add this acceleration velocity onto it, we simply need to break it down into its two component parts as well. Our resultant velocity then, so the one we get when we add the ship velocity and the acceleration velocity together, is simply found by adding our two horizontal components and our two vertical components. So this will give us the horizontal and vertical components of our new resultant velocity. And in the example on screen, I've shown that our acceleration velocity actually created a negative vertical component. Remember, going up the screen is a negative velocity. So adding those together, of course, will then reduce the resultant's vertical speed. So all of this then gives us our resultant velocity in terms of its x and y component velocities. So we need to translate this back into our overall speed and direction. And to do this again, we're going to use some of our trigonometry. So we're really dealing with right-angled triangles here. So the new overall speed is given by Pythagoras' theorem. So our new speed is the hypotenuse of our triangle. So if we square the other two sides and add them together, and then take the square root of that, that will give us our new overall speed. The direction component then is slightly more difficult. So in our triangle then, the angle we want, the tangent of that will be given by our new y speed divided by our new x speed. So if we do an inverse tangent on that fraction, then we should get our angle. But this is where it can go wrong for us. Our direction could be in any angle we want, and that could be from 0 right the way round to 2 pi radians, which is our 360 degrees. So our tangent will of course have different signs, that's positive and negative, in the quadrants round that circle. So we need to make sure that we actually calculate the correct angle and not get it wrong and put it in the incorrect quadrant. And that's where actually our language will help us out. There is actually a specific function which will do all of this for us, and that is the inverse tangent version 2, which in Lua is a tan 2, and we simply supply it our y value and our x value, and it will then give us an angle back in the range 0 to pi and 0 to minus pi. So it'll give us a plus or minus pi range, which will indicate the full 360 degrees. But if you remember, when we were doing the rotation of our vector shapes, we did actually consider the values, our angle values, going negative, and we wrote a little bit of code which would fix those and bring them back into our 0 to 2 pi range. So once we do our a tan 2 and get an angle, we'll need to use that little bit of code to just bring that angle back into our normal range. So again, just really so it makes sense to us. So that's all the theory then. So let's see if we can put that into practice and create our thrust system for our game. Okay, so in my version then, I've broken the code up into a number of different parts. So I'll take you through those as we go through then. The first thing we need to do is in our player ship function, or sorry, player ship definition then, I've added in this acceleration attribute or variable inside our object. So this is the speed for the acceleration vector. So that will give us the speed that gets added each time that the person presses the thrust button. And of course, the direction of that thrust will be given by the rotation of the ship, so the direction the ship is pointing in. So if we scroll down a bit, we'll come to the actual sort of code changes in the actual listing. So in this area here, we previously did the move point by velocity. And that was updating the player ship position. But what I've done now is I've created this new function called move player ship, and this is going to handle both the button presses for the thrust, adjusting all those velocities, and then updating the position of the ship. So it's going to handle the entire moving of the player ship in that one function. So if we come down a bit then and have a look at what that does. So we have our move player ship function here. Okay, so we get this called every go through our tick. So what we're doing is we're checking here if the up arrow key is being held in, then we will give the player ship a little bit of thrust. And once we've done the thrusting bit in this loop, or in this conditional statement, then after that we will know what velocity that the player ship is currently moving in, and we can do that movement of the position. So this is where we call our move point by velocity function again, and that's where we were before. So really then, this is the next bit that I've added into the system, which is the ship thrusting function. So if we come down here, we'll see now that we have that ship thrusting. And what we need to do is we need to create our acceleration velocity object and then add that onto the ship velocity. So we're doing here, we're creating a local acceleration, and that's going to be equal to one of our Lua tables. So we're going to make it into an object. We know that our velocity objects then have to have a speed attribute and a direction attribute. So the speed then, that's taken from that new acceleration variable that I've put into the player ship object. And again, I've put it in there so that we can, if we ever need to change it, we can just change that one place, that one definition, and anywhere where we're using this acceleration value will then be updated. And our direction for our acceleration then is the player ship rotation value. So that's the angle the ship is currently pointing in. So we're then saying the player ship velocity, we're going to change it. So we're going to update its value with this new add vectors function. So I've created this function called add vectors. We give it two vectors. So one is going to be the current velocity of the ship, and one is going to be this new local variable I've defined just up here, which is the acceleration. And we know that our resultant velocity, so the new ship velocity, will simply be those two added together. And that's what this function add vectors is going to do. And what I want you to get the hang of here is I'm breaking this down into lots of little steps. So I've created a thrust function, I've created an add vectors function, and so on, so that each little function here is only a few lines long, so it's quite easy to understand. And doing that makes your code both easier to write and also then easier to fix when you come back to it. Okay, so just a little bit of a hint there on sort of programming technique. So let's have a look at our add vectors function then. So we know that it accepts two vectors. Okay, so we saw in our calling position up here, we send in velocities and accelerations, but this is going to be just a general purpose. We can send any two vectors into the system and it will then add them together. So we're saying here then that our vector1 component is going to be equal to this new thing I've created called getVectorComponents. So remember, we needed to split up each vector into an x component and a y component. So we're going to be doing that a number of times, so I've split that out into its very own function. So I can call this function, I can pass it a vector, and what this function will do, if we go down and have a look at that, so here we have our definition. So we get vector components, we pass it in a vector, and what it will do this creating an x component and a y component. Okay, so any vector we pass in, we're assuming it's going to have a speed and a direction. And again, this is back to where we already had this bit of code before, where we could create our x component is the speed times the cosine of the angle, and our y component is the speed times the sine of our angle. But what we're now doing is we're combining those two bits into a new little object called components. And again, we're using our Lua table to do that. And we say, let's create two attributes inside that object. So we've got our x component and our y component, and then we're going to send that back to our calling function. And really what this lets us do then, we can only send one thing back in a return call. So by making a little object which contains a number of variables, we can pass this whole block back to our calling function. So if we go up here then, this is where we called it from. So we've now said our vector1 components will be equal to the components derived from vector1. And remember, getVectorComponents, that function will return us back an object which has got an x component and a y component. So this variable now will be an object containing an x component and a y component. And the same then for vector2. And all we have to do then is our resultant's x component is going to be the sum of the two x components from our vector1 and vector2. So I just scroll across a wee bit there. And our resultant's y component is simply vector1's y component plus vector2's y component. That then gives us the x and y components of our resultant vector, so the addition of these two vectors. But we need to turn it back into, pardon me, turn it back into a speed or a magnitude and a direction. So what we're doing here is I've created another function, because again this turning x and y components back into vectors is probably something we're going to have to do in a number of places. So I've made its very own function here. So we do this, call this function, we pass it in an x component and a y component, and what that will do, it will turn that into a vector and return it back so we can catch it in this local variable. And again, that's what we're going to then pass back to the calling function. So our calling function will receive back an actual velocity vector, which is the addition of these two input vectors. So let's have a look at this components to vector function, which is just down here. Okay, so component to vector, we pass it in an x component and a y component. And this is where we do our Pythagoras thing. So the magnitude or the size of our vector is given by this Pythagoras equation. So we square each of the components, add them together, and then take the square root. So that gives us the hypotenuse or the resultant vector. And then our direction then is going to be using this arctangent version 2, which is the special one which lets us turn a y component and an x component into a direction. We then construct our vector. So our vector, we give it a speed, which is going to be this magnitude, and a direction, which is going to be this direction. And then that's what we return back to our function. Oh, and one thing I've just spotted which I've forgotten to do is this direction, of course. So our math.atan2 function will return us an angle which will be in the range minus pi to positive pi to give us a full 360 degrees. But again, those negative angles are ones which we've been trying to just filter out, not because they're wrong, but just because we want to keep it in the 0 to 2 pi range just for ease of understanding. So we did do a function which was called keep angle in range. So what I need to do here then, I need to take my direction value and I need to keep it at the angle in range and give it that direction value there. Oh, sorry, give it direction. So what we're now saying is we calculate the new direction for this vector by using this math.atan2 function. Then we will make sure that that angle that we have, we then put it back into the 0 to 2 pi range with this function, which we wrote before, so we know that that's already working. And at that point then we can construct our vector and return that back to our calling function. So going back up to where we called this from, so we go up here and that's what we did here. So this is where we were adding our vectors together. So we call that components to vector function. It adds those, converts those two components into a final vector and returns that then back to the calling function for this particular function. So if we go back up here, so up to our player ship thrust one. And again, that's what we said then. So our player ship velocity now should be being updated to this add vectors function. So that should now give us the player ship velocity with this new acceleration added onto it. So that should be all of the code we need to get it running. So let's just see if that works then. So Control R and run that. So we now have our ship sitting there, and I've set the up arrow key then to be this thrust. So if I give it some thrust, we should start it moving. I should be able to turn the ship round and then thrust it back in the opposite direction. And now just move it around, and you can see now that we are doing a true sort of vector addition to this velocity. So it is acting like a true sort of thrust engine at the back of our ship. So we can rotate and then thrust off in a different direction. But we are still then keeping some component of the old velocity in there as well. Now, at the moment, our ship, once it starts moving, it will just continue to move forever. So really what we want to do now is to add a little deceleration into it. So once it starts to move, it will just gradually slow itself back down again. So let's add that in next. So because of the way we've modelled our velocities, this one should be quite easy. So if we come back up to the very top of our code then. So again, our player ship then will need some sort of deceleration. So let's add it in here. And let's call it deceleration. And we're going to set it equal to something a bit less than the acceleration. And again, we'll be able to fine tune that as we go through. So we've added in this new variable inside our object. So when we come down to move our player ship, So again, all of our movement is going to be handled in this area here. So let's come down to that function, if we can find it down here. So move player ship. Okay. So our player ship then, we give our player ship a little bit of a thrust if it's called for. And at that point then, we have a new velocity for our player ship. But what we need to do now is we need to just start to decelerate that. So all the time we call this move player ship function, we're going to be moving, but we're also going to be decelerating our velocity. And the only thing we need to do to decelerate is to simply reduce the speed. We don't need to worry about the angle at all. So what we'll do here is we will say our player ship dot velocity dot speed. We're going to set it equal to then, so we're going to update it. So we're going to copy that and tab that in. So our current speed minus then our player ship dot deceleration. Deceleration. Now we obviously don't want it going backwards, so we're going to say if, and then we're going to take, sorry, that one there, player ship dot velocity dot speed. So if it goes less than 0, then we're going to set it equal to 0, and we're going to end that if statement. So basically, we come in, we do our thrusting bits and pieces and change the velocity that way. We then decelerate the velocity. We check if it's gone below 0, and if it has gone below 0, we just then limit it to 0, and at that point we can finish off doing our ship movement. So let's see how that works then. Come in here, we start accelerating, and it now decelerates. So I can go up here, I can accelerate, and our ship then slowly decelerates. And again, in our game, we're going to have to play about with that deceleration to make sure that our ship handles itself correctly around the asteroid. So these are all things we can tune. But we now have a ship which moves, rotates, and decelerates and gradually comes to a halt. So we've reached about the half-hour mark on this lesson, so we're going to start wrapping it up. But there's one more thing I want to do while we're here. So at the moment, when we move our ship, if it goes off the edge of a screen, it goes off the edge of a screen. We have to sort of try and get it back here that way. But in the real Asteroids game, what will happen is when you go off the edge of one screen, you'll wrap around and then reappear at the other edge. And same with top and bottom. So we have a true sort of wraparound screen for both our player ship and our asteroids. So let's just quickly add that into our system. So if I go back into my code then, we've got our function here where we're moving our player ship, and at this point we update the position of our ship according to this velocity. So after we've updated the position of our ship, what we really need to do then is to make sure that we handle this wrapping system. So what we'll do is we will again update our player ship velocity, or sorry, our player ship dot position. And we're going to make it now equal to another function, which will be wrap position. And we will give that then a position itself. So player ship dot position. So we're going to make a new function called wrap position. It's going to receive a position object. And what it will do then is if that position has gone off the edge or the top or bottom of the screen, it will then wrap it round to the other side. So what I'm going to do with this one here, I'm going to, at the very top of my listing, I'm going to define two constants which are going to be the size of the screen. And again, I don't know that off the top of my head, so I will find that out in a second and show you. And then we're going to write this function itself. So it needs to accept in a position object. So remember, that's got X and Y components. And it will then return a position object, which we can then catch in our playership.position. So why don't you have a go at writing that one, and I'll see you in a few seconds. Okay, so let's have a look at how we do this then. So I've created two constants. So again, in Lua we don't actually have a real constant declaration. So these, although I'm saying they're constants, we can change those if we needed to, but by giving them a variable name in full capitals, that sort of is a general sort of way of notating that these should actually be treated as constants, so they shouldn't change. But the values then, so in tick 80, the screen is 240 pixels wide and 136 pixels deep. So that actually means that the pixel values go from 0 to 239. So 240 is the first pixel which is off the edge of the screen, and similarly 136 is the first pixel off the bottom of the screen. And again, we'll have to play with that when we come down to do our test later on. So I've defined them here so that if the resolution ever does change, we can just change it here, and as long as we're using these constant values, then our code should readjust itself to that. So we said, again, if we go down to our move player ship function, which is somewhere here. Okay, so our move player ship. So we said we were going to write this function called wrap position, which is going to take back in our position and then send us back the wrapped version of the position. So I've done that down the bottom here. So this is our code now for wrap position. So again, it's receiving in that position. And really what we're saying is we're checking all of the coordinates. So if our x coordinate is greater than or equal to screen max x. So this will allow us to get up to 239, but as soon as we hit 240, that will then say this is a wrap condition. And if it's a wrap condition, we simply set it back to 0. So our ship will head towards the right-hand edge of the screen, get to 239. When it hits 240, it will then flip back across to our left-hand edge. And similarly then, if it goes off the left-hand edge, we will flip it over to the right-hand edge. And again, our screen max x position -1 is the first visible pixel on the right-hand edge of the screen. Top and bottom then is exactly the same way. So if it goes greater than or equal to our screen max y, then we set it back to 0. And if it goes less than 0, we then set it back to our screen max y -1. And again, max y -1 is the first visible pixel at the bottom of the screen. And then we simply return back our position object. So really that should be enough then to make that work. So if I do Control R and run that, and back in here, if we head off the top of the screen, we should then reappear at the bottom. Head off the bottom, we should reappear at the top. And then off to the side, we should wrap around and back again and wrap around. And again, if we go diagonally again, we should then find that our ship is doing its sort of wrapping around system. And there we have our player ship movement now fully modeled, but again with all of the code now written so that when we come to produce our asteroids, all of the movement code for moving and rotating and drawing asteroids should all be there. And I'm hoping that that's what we'll do in the very next lesson. But that's going to wrap it up for this lesson. So let's get out of there. Let me make sure I save my code. Make sure that's saved. And I hope you're enjoying it, and I will see you in the very next lesson. And bye for now. Don't forget to visit the course pages for this project. There you'll be able to download the code for this lesson and get lots of extra hints and tips. You'll also get access to all my other programming, electronics and gaming projects. All the links are in the description below. For more games programming, electronics projects and retro gaming, please make sure you like this video, subscribe to my YouTube channel and visit my website.